So last time we saw an application of regularity lemma, the multicolor version, in graph Ramsey's theory. This is a theorem by Vartal, Rerdel, Samrady, and Trotter, saying that the Ramsey number for graphs with bounded degree is linear in the order of the graph, rather than exponential as in the complete graph case. Then we went on to talk about this Russo-Samarady's triangle removal lemma, of another very important lemma related to regularity lemma. So let's recall Russo-Samarady's triangle removal lemma and see some applications today. So Russo-Samarady triangle removal lemma. I will state the original form and its contrapositive. Both forms are useful to remember. The original form is for any graph G, m vertices. Now, if the number of triangles is little o of n cubed, so the triangle density is 0, then we can destroy all triangles in the graph by removing a negligible amount of edges. So we can remove what is negligible, little o of n square edges, to destroy all triangles in the graph. Now let's look at the contrapositive. Contrapositive is saying we cannot remove few edges to destroy all triangles. That means there are lots of edge destroying triangles. So original is equivalent form. Contrapositive. So for any graph G, m vertices, if the number of edge disjoint triangles is linear, is quadratic. So the opposite of little o n squared is big omega of n squared. When you have a collection of edge disjoint triangles, this is edge disjoint, then for each such triangle to destroy it, you have to kill an edge for each one of them. So when you have this many edge disjoint triangles, we need to remove at least this many edges to make it triangle free. Then we will get the negation of the hypothesis, showing that this graph must have a cubic number of triangles, positive triangle density. So the first application we will see is sig3 theorem. So removal lemma implies sig3 theorem. Let's recall, I briefly mentioned the statement of sig3 theorem. So we now consider, in this setup, we consider 3 uniform hypergraphs. I will abbreviate it as 3 graph, just means 3 uniform hypergraph. Where you still have vertices, and the edges will be triples of vertices. And a hypergraph, let's recall some definition, is linear. The hypergraph is linear if no two vertices they share a common neighbor, a co-neighbor. In other words, if no two hyper edges, they share two vertices. If no two hyper edges share two vertices. Or in other words, every pair of vertices lies in at most one hyperedge. You are forbidding. We don't want this thing. Here's a hyperedge. Here's another hyperedge. They share two common vertices. This is forbidden. There's a simple proposition that's proven here. That every m vertex linear 3 graph H has at most 1/3 times n choose 2 edges. So usually, what is this proposition about? When you have a 3 graph, what's the maximum number of edges we can have? N choose 3. When by forbidding this, so maybe I put a remark. So complete 3 graph, for 3 graph, we could have positive edge density is this many edges, n cubed, n choose 3. So here, this is saying in the 3 uniform setting, write it as a two-round form. The extremal number, when you forbid these 2 edges sharing 2 common vertices, if you forbid this configuration, then you drop. You cannot be too dense. Not only you cannot have positive edge density, you drop from n cubed to n squared. The proof is very simple. Okay. So let's write DUV, the codegree of vertices UV, of U and V. What does it mean? If this is UV, then that just means the number of vertices here, this is the codegree. The number of vertices in this blue part that form a 3 uniform hyperedge with the pair UV. A simple observation similar to handshaking lemma in graph. If you sum up the codegree for all pairs, V choose 2 for all pairs, what do we get? We get 3 times the number of edges in the hypergraph. Why? For every hyperedge, it is counted 3 times. When you look at the codegree of UV, you count once. It is counted once. If you look at the codegree of these 2 vertices, it's counting 2 times. When you look at the codegree of these two, it's counting 1 more time. All right. So if E of H is bigger than 1/3 and choose 2, this will imply that sum of DUV equals to 3 times EH is bigger than n choose 2. But what does that mean? The number of summons here is exactly n choose 2 pairs. That means for some DUV, the value is strictly bigger than 1 by pigeonhole. But having DUV strictly bigger than 1, it just means that we have this forbidden configuration. This implies some DUV by pigeonhole at least 2, which is contradiction. Okay. The second definition, I mentioned it last time, is called ST configuration. This, in the 3 uniform hypergraph, this just means a set of, in a 3 graph H, this just means a set of S vertices inducing at least T hyperedges. In this language, let me give you some example. This forbidden one that we've been looking at in linear hypergraph, what is this configuration? This is 4, 2, 4 vertices and 2 edges. What about this one? Well, we have 1, 2, 3, 4, 5, 6 vertices, 3 hyperedges. So this is 6, 3. Now, we say a hypergraph, a 3 graph, is ST free if it does not contain any ST configuration. In other words, the 3 graph is linear, is linear hypergraph if it does not contain a 4, 2 configuration. There's only one 4, 2 configuration that looks like this. This is an ST configuration usually is not a unique 3 graph to forbid. There might be, let me draw another one. 6, 3 configuration could also look like this. You have 2. This is also 6, 3. Now I add one more here, right? 6 vertices, 3 edges. They look very different. So it's not a unique configuration to forbid. Now the 6-3 theorem is saying that a 3 uniform hypergraph, if does not contain 6-3 configuration, rouge I said already. Six, 3. So for any m vertex 3 uniform hypergraph H, if you 6-3 free, then the number of edges, all possible number of triples is n cubed But since you forbid 6, 3, you drop all the way from n cubed to n squared, even lower. So it's a subquadratic. Okay. We can show that the number of edges is little of n squared. Okay. We will see in a little bit, after we give a proof of this, that this little of n squared is fairly tight. There's a lower bound that's almost quadratic in n. So let's first see the proof of 6, 3 theorem. Okay. Before I give the proof, here's a remark. I'll leave it as exercise. It's not hard to see that forbidding 6, 3, look, 6, 3, you have these two configuration. Look like this or look like that. But actually, if you forbid, if you let the graph to be linear, so you don't have 4, 2 like this, then the only thing that you need to forbid, the only other 6, 3 configuration is this one. Looks like a hypergraph triangle. You have 3 edges like this, right? So 6, 3 theorem, forbidding 6, 3 is the equivalent of saying you forbid these two hypergraph. We can rephrase 6, 3 theorem as you have extremal number of when you forbid these two configuration. Then the extremal number is n squared. These two, this statement is the same thing. So we are proving a hypergraph Turan type statement. How do we go about proving such thing? Let me first say the idea. The idea is basically we can kind of assume the graph is linear. The reason being, if it's not linear, you will have two hyper edges. You will have a configuration like this. Now, the problem of having this is that now if any of these vertices, there's a hyper edge sticking out, you will get the 6, 3 configuration. So if you ever see this configuration in your hypergraph, it must be an isolated component. But such isolated component is very sparse. You can just simply remove it to look at the remaining graph. You can boost up the average degree. You still have a counter boost up the average degree. So by looking at density's subgraph in your hypergraph, you can sort of assume your graph is linear. So forget about this guy. Moving to, now we have a linear hypergraph. We just need to forbid this configuration. The idea is to look at the shadow graph, meaning for each this hypergraph, we build a graph, a two graph, where we convert each hyperedge into a triangle into our graph. Now the idea is that this shadow graph, the number of edges there is proportional to the number of hyperedges in our hypergraph. We just need to prove the shadow graph has little o n squared edges. Then we can use triangle removal lemma by saying that, oh, okay, if the edges are too many, then you must have many triangles. And many triangles will imply somehow this configuration. Let's see how this goes. So first, Let's suppose that we prove by contradiction. Suppose to the contrary, suppose false. Suppose that there exists and C such that what's the opposite of this? Is this C such that there for infinite many n? Meaning n, there is 6, 3, 3, 3 n vertex 3 graph H with number of edges to be bigger than Cn squared. So suppose we have an infinite sequence with growing order of 6, 3, 3 graph with quadratic number of edges. Now this part, I will leave it for you to make it rigorous by zooming into the subgraph with higher average degree. Which is still a counterexample. We may assume the average degree of H is the maximal of all hypergraphs that are subhypergraphs of H. Okay. The reason is, as I said, try to prove it. If so why we need this? This is to prove the graph is linear. So now this we call this maximality. Maximality of H implies that H is linear. Suppose not to see this. If you have non-linear, you have two edges sharing two vertices, then no vertices here can be adjacent to, can lie in another edge. You have a 6-3 configuration. This thing is an isolated component. By 633 this. And deleting this component, deleting this 4-2 configuration, you will boost up the average degree. But we know that there's no subgraph of H with higher average degree. Okay. Good. So we know the graph is linear. By the previous proposition, implies that the number of edges in H is at most 1/3 times n choose 2. So it's at most quadratic. We now need to boost this big O. We need to boost this big O n square bound to little o n square. Okay. The trick is we take the shadow graph of G. Consider the shadow graph G of H. What does it mean? The vertex set is the same as the vertex set of the hypergraph. And for the edge sets, we turn a hyper edge in H into a triangle in G. All right. So let me draw a picture. Suppose it looks something like this. Then how do you transform it? You turn every triangle into G. In other words, think of this hyper edge as a 3 sets. You take its 2 shadow, which are these pairs. This will be the edge of our graph. So it becomes this graph. This is a small example. Okay. In this graph G, we call a triangle. So you have a triangle. We call this triangle H triangle if it corresponds to some hyperedge in H. We call a triangle an H triangle if it comes from a hyperedge of H. Okay. The first property we want to observe about these H triangles observation is that the collection of all H triangles in G, they are pairwise edge disjoint. This is very simple. If you have 2 triangles, they are not edge disjoint. That means it looks like this diamond. 2 triangles sharing an edge in G. This is very simple, right? If in G you have 2 sharing an edge, and both of these triangle correspond to an hyperedge in G, that would have correspond to this 2 hyperedges sharing 2 vertices. And it's not linear. So we don't have 2 H triangles in G sharing an edge. They are edge disjoint. Good. What do we know? We suppose our hypergraph has quadratic number of edges. Every such edge, since it's linear, every such edge corresponds to 3 edges in our graph G. And different triangle, different hyperedges in H correspond to different set of 3 edges. So this implies, edge disjointness implies this is basically as H is linear, right? And also observation, H is linear implies the number of edges G equals to 3 times the number of edges of H, which is bigger than 3cn squared. Now we can apply triangle removal lemma, the contrapositive form, saying if a graph has many edge disjoint triangles, here recall the number of, this implies the number of edge disjoint triangles in G is at least the number of H triangles, which is E of H bigger than Cn squared. The contrapositive form of triangle removal lemma is saying when you have quadratically many pairwise edge disjoint triangles, then your graph must contain cubic number of triangles. By triangle removal lemma, this implies here, triangle removal lemma implies the number of triangles in G is at least some an cube. Is qubit. Okay. And when n is sufficiently large, this is bigger than Cn squared, which is not bigger than Cn squared. It's bigger than this thing because H is linear, so it's bigger than quadratic. This is roughly what n squared over 6, bigger than n squared, bigger than E of H because H is linear. Now we arrive to our final contradiction. What does it mean the number of triangles in G is more than the number of hyperedges in H? Remember, hyperedges in H is in one-to-one correspondence to H triangles in G. So that means there is a triangle in G that does not correspond to a hyperedge. So thus, there is a triangle which does not correspond to a hyperedge. It's not an H triangle. But what does it mean? It's not an H triangle. Let's draw the picture. You have in G. Now let's look at the situation in H. This triangle is not an H triangle. Let's look at these three vertices, X, Y, Z. They have the same vertex set, so you have X, Y, Z here. XZ is an edge in G. That means it's a shadow of some hyperedges in H, meaning in H, they have a hyperedge containing X and Z. But this hyperedge cannot be XYZ, because if this is the hyperedge containing XYZ, then this would have been a H triangle. So triangle, let's say XYZ. X, Y, Z, XZ shadows of hyperedges. This implies we have a hyperedge containing xz, and this other vertex is not y. Similarly, we have these two is contained in the hyperedge, and the third vertex cannot be this vertex because otherwise this will be not linear. So it must be a new vertex. Similarly, this one is contained in the hyperedge, and the third vertex must be a new vertex. Otherwise, you will obtain a nonlinear hypergraph. At the end, this will correspond to, we will get a 6-3 configuration as above, contradiction. That's it. Okay. So this is the non-H triangle that's coming from 3 hyperedges corresponding to 6-3 configuration. Okay. This theorem, if just by itself, looks a bit strange. Why we consider 6-3 configuration, this type of Turan statement? One of the original motivation is because this theorem was used to prove a number theoretic statement, a classical theorem of Roth, on the largest set of integers without 3-term arithmetic progression. So let's see this part. Sig-3 theorem implies Roth theorem. So what is Roth theorem? We say a set of integers, natural numbers, say, whatever, is 3AP free if it does not contain any 3-term arithmetic progression. So that looks like A plus D, A plus 2D. This is 3-term arithmetic progression. AP stands for arithmetic progression. Now the question is, if you have a subset S, say, of the first n integers, that's 3AP free, then how large can it be? How large can a 3AP free set be? Roth proved that such sets cannot have positive density in n. For any delta bigger than 0, there exists n naught, depending only on delta, such that for all n, at least n naught, for any 3AP free S in n, we have S is of size delta n at most. In other words, if you forget about this quantifier, just says that 3 in the concise form, 3AP free implies the size is little o n. Okay. Good. Now, at the first glance, what we have proved that this C3 theorem, it seems to have nothing to do with this number theoretical problem, the 3AP, a set that's not that not containing three-term arithmetic progression. So this clever proof of reproof of Roth theorem by Rusha-Samarady is to observe that we can construct some auxiliary hypergraph where three-term arithmetic progression somehow corresponds to a 6-3 configuration. Then we can use, we will construct the idea is we will construct an auxiliary 3 graph in which 3AP corresponds to 6-3 configuration. Okay, and then using the bound on 6-3 configuration on the number of hyper edges in the 3 graph, we can then get the bound on the size of a set without 3AP. So let me actually rephrase this in this way. Let's say for any set S, subset of n, now if the size of S is bigger than delta n, then S contains 3AP. Contains a 3-term arithmetic progression. Here's the proof that 6-3 implies Roth So the hypergraph we are building is like this. And we're going to build a uniform three-party hypergraph. So the three part of the vertices is respectively the first n integers, that's the first part, first two n integers, second part, and first three integers, the last part. And what do we have? We have a set so suppose the contrary, suppose we have a set S that's 3AP free, but the size is delta n. I forgot to say this. Suppose exists 3AP free S. Oops. Of size delta n. Good. We have the vertex set down. All the edges, 3 hyper edge will contain one vertex from each part. How do we build the edges? For this is the vertex set. For the edge set, let me call it H. It looks like this. For every x in the first part, and for every a in S, we will build a hyperedge x, x plus a, x plus 2a. Like, so every hyperedge corresponds to a 3-term arithmetic progression. This is our that's our hypergraph. What's the number of edges? Well, the number of edges equals to, we have n choices for x. You can choose anything here in the first integer. And we have s choices for this common difference of the 3AP. So this is delta n squared. S is of size delta n, right? And one quick word, why is equality here? Because for every different x and a, the resulting hyperedge are all different. It's uniquely determined by these two. Okay. As x plus 2a is uniquely determined as the third vertex, which is this x plus 2a, is uniquely determined by the first two, which is x and x plus a. This also implies that H is a linear hypergraph. Okay? If you fix x and x plus a, there's only one 3-term arithmetic progression containing this pair. So you cannot have two hyperedges or two 3AP sharing two elements. This is because no 2 3AP sharing two elements. Here, hyperedges correspond to 3APs. Okay. So, to finish the proof, we will show that, well, EH is of quadratic size by 6-3 theorem, since it's linear. 6-3 theorem says for every linear hypergraph, you will contain this 6-3 configuration. Since your number of edges is not little o n squared. So all we need to do now is to show such 6-3 configuration will give you a 3-term arithmetic progression in S, which will give us the final contradiction because S was 3AP free to begin with. So that means at the very beginning, we cannot have a 3AP free sets of positive density. Suffices to show by 6-3 theorem, H contains the 6-3 configuration because you have quadratic number of edges. Suffice to show that we are left to show this 6-3 configuration corresponds to 3AP in S. Okay. Now all we need to do is to see how this 6-3 configuration, and since H is linear, this 6-3 configuration has to look like this, right? 6 vertices and 3 hyperedges, like look exactly like this. There's no other way. So let's first analyze how these 6 vertices distribute over these 3 parts of the hypergraph. Well, there are only two possibilities. The two possibilities. Every edge spans, take one vertex from each part. So every part should contain at least one vertex. Either you have 2 vertices on each part, in total 6 vertices in the 6-3 configuration, or you have 3-1-2 configuration. Here, just by symmetry, I assume 3 in the first part, but you can do similarly, or 3-1-2 like this, or 3-1-2 like this. You take all permutation. So the distribution has to be 2-2-2 or 3-1-2. Let's first see that 3-1-2 is impossible. Only 2 possibilities. To distribute 6 vertices to 3 parts. So 1 is 3-1-2 or 2-2-2 vertices in each part. So let's see case 1. Let's draw a picture. You have n, 2n, 3n. Okay. If it's 3-1-2 without loss of generality, the other cases can be proved similarly. Let's assume we have 3 like this. Also, let's give name to this 6-3 configuration, shall we? Let's give name. We have 3 hyperedges in this 6-3 configuration, and each hyperedge corresponds to a 3AP. So let's assume these 6-3 in H are called X, X plus A, X plus 2A, Y, Y plus B, Y plus 2B. These 3 hyperedges, 3 arithmetic progression, Z, Z plus Z, Z plus 2C. Okay. We have these 3. So if it's 3-1-2 distribution, so we have 3 points, X, Y, Z. They share all the same vertex. Okay. You have 2 vertices at the end. So they have to look something like, you have the blue one. Oops. And you have the green one. Green also have to use this vertex, but you cannot use the top right vertex anymore. It has to, why is it? It has to look like this, right? Wait. Let me use a smaller one. Where's the blue? So the first one, second one, you have to use the middle vertex, but you cannot share 2 vertices. This is linear hypergraph, so you have to go below. Now look at the third one. The third one goes here, but you cannot go anywhere. Because if you go anywhere, you will get a non-linear hypergraph. Okay, so this is impossible. This will imply not linear. So we just need to focus on the second case. The second case, 2 vertices on each part. First case. Two vertices on each part. We have to draw them in such a way that it's linear. So let's try the blue one, let's say like this. First one, there's no restriction. The green one, okay. The green one, we have two choices. Either you use this vertex or you don't. It's you will see it will be the same. So let's just use a different one, let's say. Now you use a wait, give me a second. Yeah, all cases will be similar. So I'll just do a particular case. Let's say you also use the first one. But then the other two must be disjoint, right? Because of linearity. Now the third one, how can it look like? The third one, well, you cannot use the same vertex anymore. Because if you use the same vertex, you cannot go anywhere. Go here, you share 2 vertices with blue. Go here, you share 2 vertices with green. So you have to use this vertex. And then you can either go here or go here, doesn't matter. So if you go top, then you have to go bottom. Otherwise, you share 2 vertices with blue. So that's one possibility. Let's try it. Looks like this. Now we can write out all this relation. The blue one is x plus a, x plus 2a. But x plus a is also z plus c, right? This is z. This is z plus 2c. X equals to y. This is y plus b. This is y plus 2b. You just write out all. If 2 vertices collide, we have x plus y, x plus a equals to z plus c, y plus 2b equals to z plus 2c. Okay. Good. Any other? That's it. 3. So now I want to do is, what I know is A, B, C, they are elements of S. I want to prove that A, B, C will form a 3AP in S. So let's see, how do I show that? It's probably x equal to y. So let's just change this to y. Wait, did I make a mistake? X plus a, x plus 2a, y plus b, y plus 2b, z plus z plus c, z plus 2c. So z plus 2c equal to y plus 2b. That seems to be correct. So let's see. This is y. So y minus z is c minus a. And y minus z also 2c minus 2b. So these two are the same. Now, that implies 2b equal to a equal to c. Okay. So this is the same as I just plug in y. Y plus y and x is the same. So y plus a is z plus c, which is the same as y minus z is c minus a. Okay, where here y minus z is 2c minus 2b. So we have 2c minus 2b equals to C minus A, which is the same as A plus C equals 2B. So this is a 3AP. All right. Notice that why this is a 3AP? Because A is not equal to B. If A equals to B, what will happen? We still need to prove that. Wait. If A equals to B, these two vertices will collide. So it's not a linear hypergraph. Okay. Linear hypergraph implies A is not equal to P, which implies this contradiction. Any question? Now, there's a remark I want to give here. Remark is that this bound is fairly tight. In this above proof, we actually see that this set S is 3AP free if and only if the corresponding hypergraph that we constructed H is 6-3 free. This is equivalent. So there was a construction by Beheron constructed exist the 3AP free sets. And remember, E of H is roughly n times the size of S, right? It's exactly n times size of S. Now, Beheron constructed 3AP free sets of size n squared over e to the some constant times square root log n. This thing is bigger than any n to the 2 minus epsilon for any epsilon where n is sufficiently large. So this is n to bigger. This bound is larger than n to the 2 minus epsilon for any epsilon when n large. Okay. In other words, this little o of n squared bound in 633, we cannot improve it to n to the 2 minus epsilon for any epsilon. So the number, the quadratic exponent 2 is optimal. Now I want to introduce a basically equivalent form of 6-3 theorem, but in graph theory term. It looks quite different at first glance, but it's essentially equivalent. Okay. 6-3 theorem is about 3-uniform hypergraph. What is this equivalent form in graph term? We need the terminology. So this is about equivalent form is induced matching. Let's first give a definition. We have a graph. In a graph, we know what is matching. It's a collection of vertex disjoint edges. Now we call a matching M in the graph G, and induced matching if the induced subgraph has no other edges than those in M. Okay, in other words, if you look at the subgraph, if you look at the vertex set of the matching, you look at the induced subgraph on those vertices of the matching, the edges there, you only see the edges in the matching M. Let me draw a picture. Okay. Okay, so this is our graph. This is our graph. Now we have two. One is this guy. Look at, this is a matching of psi 3, but it's not an induced matching. Let's call it M prime. We have another matching, M. Where are they? Okay, this is my M. Both of them are matching of psi 3, but M prime is not. M is induced matching. M prime is not induced matching. Why? If you look at these 6 vertices on M, now you look at the G graph edges on these 3. You only see the M edges, the edges in the matching. So it's induced. But if you look at the M prime, these vertices, these 6, apart from the 3 red edges in M prime, you also see these blue edges in M and also this edge in G. So you have additional edges on the vertex set of M other than those in the matching. M prime is not. Okay. Now we can state the theorem, induced matching theorem. Which is the equivalent form of sig3 theorem, but in terms of graphs, induced matching theorem. For any graph, if an n vertex graph is a union of n induced matchings, then, in other words, the edge set of G is the disjoint union of mi, n of them, and each mi is induced matching in G. Okay. then the graph G cannot be dense. E of G is little o of n squared. We will see, there are two things we will see. First, I will leave you exercise. It's not hard to show. Similar to how we prove Roth theorem from 6-3 theorem, you can also derive 6-3 theorem, Roth theorem from induced matching theorem. So prove Roth theorem that every 3 AP3 sets in the first n integers has little o n size using induced matching theorem. And what we will see here is a theorem that induced matching implies 6-3. Okay. So what's our goal? Prove let H be an n vertex 3 graph. That is 6-3 free. Our goal, as in the 6-3 theorem, is to prove that EH is little o n squared size. Okay. Again, by passing to subgraphs with largest average degree, we may assume our graph H to be linear. M vertex linear hypergraph, so you don't have two hyperedges sharing two common vertices. Good. Now we have a linear 3 graph. 6-3 free means there is no this configuration. Linear is triangle free. We want to prove little o n squared. I've already told you that we're going to use induced matching theorem. So somehow we have to construct the graph whose edge set is the union of induced matchings. And this is how we do it. First, we convert H into 3-part type 3 uniform hypergraph while retaining positive fraction of edges. This is easy just by taking a random partition. So take a random equipartition. Equipartition means each VI is of the same size. So V1, V2, V3. Okay. And the edges is called the cross edge if it contains exactly one vertex from each part. Then the expected number of cross edges is what? It's not hard to show that it's 2/9 times the number of edges in H. Why? For every edge, right? The first vertex goes somewhere. Let's say it goes to V1 for every edge in H. You have an edge, right? This first vertex goes here. Now, second vertex, it has to go to two other parts. The probability is 2/3. Once you go to, let's say, this part, the last vertex is nowhere but go to the last part, which is probability 1/3. So for every edge, the probability its cross is exactly 2/9. And here we use linearity of expectation. That means there exists, if the expectation is 2/9, that means there exists a partition of equal size into 3 parts, such that the cross edges is at least the expectation. So there exists a partition V1, V2, V3 with, let's call H prime is the induced 3-party graph, having number of edges 2 9s times the number of edges of H. Okay. We are going to build a graph now using H prime. How do we build it? So this is our H prime, 3-party linear 3-unit hybrid graph. And basically, we're just going to take the length of vertices in V1 and take their union. We'll let G to be union of lengths of vertices in V1. In other words, what I'm saying is you let's call V1, the vertices V1, V2 to V, I don't know. Equipartition, right? So this is Vn over 3. Okay. So I call Mi is what? The length of Vi. What it means is, so this is Vi. You look at all those pairs that form an edge with Vi. So this is the length. And notice that Mi is a matching. That's easy to see because H prime is linear. So Mi is a matching. But also, we need to notice that, so what is G? G is the union of Mi. I goes from n to n over 3. Okay. Also, we want to notice that each Mi is an induced matching. So let's prove it. If it's not induced matching, what does it mean? That means you have right, this is your Vi. That means on the vertex set of this Mi, you see some other edges than the blue matching edges. And these edges must use two vertices in the matching. So let's say these two vertices. Draw a picture. Now you have some other edges than the matching edge. Yeah. And these other edges corresponds to coming from the link of another vertex, let's say Vj, a different one. We have a problem, right? The problem is we now have this edge, this edge, and this edge. Okay, we have a 6-3 configuration, 6 vertices, 3 hyperedges. That's a contradiction because H prime is a subgraph of H. It does not have 6-3 configuration. Okay. So I will now write the proof of this observation. It's basically by this picture. Yeah. If you have a non-matching edge, it must come from another vertex Vj, then you have 6-3 configuration. So let me just write as not induced implies 6-3 in H prime, which is a contradiction. Good. Now we are done. Why? So we have G is the union of n/3 induced matchings. Then induced matching theorem implies E of G is little o of n squared, right? But what is E of G? Each matching is precisely the degree of each vertex. So the size of the matching is degree of vertex. And when you take the union of all matching, it's the sum of degree of vertices in the first part, which is exactly the number of edges in H prime. So in other words, E of G equals to E of H prime. But E of H prime is bigger than 2/9 of E of H. That's how we take it. And this is little o of n squared. Solving this, you will see that E of H is also little o n squared. We are done. Any question? Time is almost up. I will prove induced matching theorem next week. Next week will be the last week of the this course. We'll have 2 more classes. But next week, so announcement is next week the class would be in the afternoon. So there will be a change on the time. I will announce the change on the course webpage. So please check it this weekend to see the updated course time. So let's recall what we did today. Today, we prove 6-3 theorem using removal lemma. Okay. And then we use 6-3 theorem to prove Roth theorem about 3 AP free sets. And then we mention induced matching theorem and use that to prove 6-3 theorem. So today we have triangle removal lemma implies 6-3 theorem. And 6-3 theorem, we use it to prove a number theoretical statement, which is the Roth theorem. We also introduced the induced matching theorem And we see that induced matching theorem can be used to derive 6-3 theorem. All right. Next time we will prove this statement. Any question?